In 1987, the 12 member states of the European Space Agency decided to develop a new launcher, Ariane 5, with greater lift capability than Ariane 4 for launching both satellites and space station elements. Ariane 5 development is a program of the European Space Agency, which has overall responsibility for its execution. ESA has delegated the program's management to CNES, the French National Space Agency. Ariane 5, with a total liftoff mass of 735 tons, will operate from Europe's spaceport in Kourou. Total thrust, 1,200 tons. It's designed to place payloads of up to 6,800 kilograms for single launches and about 6,000 kilograms for dual launches in geostationary transfer orbit. With a reliability factor of 0.985 and a cost below the figure for the Ariane 44L version, the new launcher is capable of all types of space mission. Increased mass application satellites, scientific satellites, space station elements, interplanetary probes, space transportation vehicles. Ariane 5's total height varies from 46 to 56 meters. It has a dual-stage lower composite comprising the cryogenic main stage burning liquid hydrogen and liquid oxygen, and two powerful solid propellant boosters. The two boosters provide 92% of initial thrust on liftoff. The configuration of the upper composite varies according to the flight mission. For simultaneous injection of a number of satellites into geostationary transfer orbit, which will be Ariane 5's most frequent mission, the upper composite comprises a vehicle equipment bay, a single-engine storable propellant stage, a Speltra multiple launch bearing structure, and a short fairing. Nearly 150 companies and organizations and over 6,000 people were involved in the Ariane 5 development program. The launcher system was developed under the responsibility of the industrial architect in France. Extensive tests were carried out at the Ariane 5 functional simulation facility, with particular emphasis on tests designed to check the performance of all systems contributing to the attitude control and guidance function and validate integration of the launcher's electrical systems. The cryogenic main stage has a diameter of 5.4 meters and a height of 30.5 meters. It's powered by the Vulcain engine, which delivers 110 tons thrust in a vacuum. The main stage principally comprises a forward skirt housing most of the functional electrical equipment for the stage, common bulkhead tanks containing 25 tons of liquid hydrogen and 130 tons of liquid oxygen, burnt in just 10 minutes, an engine thrust frame, and the Vulcain engine. The main stage forward skirt, manufactured in Germany, takes up the thrust of the two solid propellant boosters and carries the upper composite. The tank bulkheads in aluminium alloy are also manufactured in Germany. The cylindrical sections of the tank are made in France. The component elements of the tank are welded together in a dedicated industrial facility with a surface area of 14,500 square meters. The main stage tank structure accounts for 2/3 of the launcher's total height. When empty but fully equipped, the tank has a mass of only 5,630 kilograms. The thrust frame acts as a mechanical interface between the cryogenic tank and engine. Manufactured in the Netherlands, this frame carries the propellant and fluid circuits and equipment for operation of the cryogenic stage. The engine systems are produced in various European countries under the direction of the Vulcain prime contractor. The oxygen turbopump and solenoid valves in Italy, the hydrogen turbopump, gas generator and helium spheres in France, the combustion chamber in Germany, the nozzle in Sweden, the propellant circuits in Austria, the engine actuation and hydraulic generator unit in Belgium, and the main electrical equipment in Norway, Denmark, Belgium and France. The Vulcain engine is integrated in France. The cryogenic main stage is assembled in a new building with a surface area of 6,000 square meters and a maximum height of 50 meters, constructed specially to cater for the massive dimensions of this stage. In this building, pre-integration of the forward and rear structures of the main stage takes place. Final assembly is done in large bays, and about 3 months are required to assemble each stage. The facility is designed for a production rate of 8 main stages a year. Development and qualification of the Vulcain engine involved substantial investment. 5 engine and subsystem test stands were built in France and Germany. Since 1985, over 800 engine sub-assembly development tests have been conducted using these facilities. The first tests on the complete engine took place on the PF50 test stand at Vernon in France in July 1990. A second test stand was later commissioned at Lompoltshausen in Germany. Testing of the Vulcain engine, which is now finished, involved 278 tests on 13 engines with a total burn time of 87,000 seconds. The Vulcain engine and all its components and structures were qualified on the ground in 1995. The functional engine tests were accompanied by mechanical and vibration resistance testing. Each Ariane 5 solid propellant booster is 3.03 meters in diameter, stands 30 meters high, and has a lift-off mass of approximately 270 tons. Each booster comprises an inclined forward cone transmitting thrust to the launcher's main stage core body, a cylindrical part made up of 7 steel sections and containing the 3 solid propellant segments, a rear skirt interfacing the launcher with the launch table, and a nozzle with a flexible bearing providing thrust deflection of up to 6 degrees. Each booster engine delivers approximately 540 tons thrust on liftoff. Booster production is carried out in Belgium for the rear skirt, forward assembly, and hydraulic thrust deflection actuators, Germany for the steel casing elements, Norway for the forward and rear devices attaching the booster to the main stage, and for the post-separation distancing thrusters, Italy for assembly of the internal thermal protection on the 3 booster segments. Production and casting of the 23 tons of solid propellant for the forward segment. And manufacture of the igniter. France for manufacture and assembly of the nozzle. The nozzle assembly is approximately 5 meters high. French Guiana for production and casting of solid propellant for the central and rear segments, each with a mass of over 100 tons. A fully automated grain production plant has been built for reasons of safety and logistics on a special site not far from the launch complex. And also in Kourou, in the booster integration building, for nozzle assembly, the booster development and ground qualification program was conducted on a dedicated vertical test stand in Kourou. The first battleship test took place in 1993. The engine and stage development and qualification tests were performed in 1994 and 1995. The upper composite is mounted on the cryogenic main stage. It has an outside diameter of 5.4 meters and a maximum height of 20 meters. At its base is the vehicle equipment bay. With a height of 1.56 meters and a mass of 1,380 kilograms, the bay contains the launcher's main electrical and data handling systems, in particular the onboard computers containing the flight program which directs the guidance and attitude control function, stage separation procedures, etc. Manufacture of the vehicle equipment bay clearly reflects wide-ranging European participation. The structure is made in Spain. The attitude control thrusters and tanks in Germany. The computers in Sweden. The inertial guidance platforms in France. The flight control electronics in Denmark. The hybrid circuits in Norway. The electronic sequencing units in Spain. The launcher control and checkout systems in Belgium. With development and integration of the vehicle equipment bay in France. Mounted on the internal bay structure, the storable propellant stage carries 9,700 kilograms of propellant for a geostationary transfer orbit mission and burns for 1,100 seconds. This stage delivers 27.5 kilonewtons thrust in vacuum. The structures are developed and manufactured in Spain. The propellant tanks, servo actuators, and propellant feed valves are made in Germany. And the engine attachment gimbal device in Norway. The Istus engine combustion chamber uses technology derived from the cryogenic third-stage engines for Ariane launchers 1 to 4 and is manufactured in Germany. Integration of the stage with its equipment is also carried out in Germany. Qualification testing of the complete stage was performed in 1995. A series of other mechanical tests on the bay and stage was also run, including vibration tests in particular. Mounted on the vehicle equipment bay, the Ariane 5 Speltra multiple launch bearing structure has a diameter of 5.4 meters and a mass of 825 kilograms. The Speltra is manufactured and assembled in Germany. A number of structures were built for development and qualification tests. All mechanical and separation tests were performed in 1994. Capping the Speltra structure, the ogival short fairing used in the dual launch configuration has a diameter of 5.4 meters, a height of 12.7 meters, and a mass of 1,800 kilograms. The long fairing has the same diameter, a height of 19.2 meters, and a mass of 2,800 kilograms. Like those for all previous Ariane versions, the fairings for Ariane 5 are manufactured in Switzerland. The various fairing components are made of carbon. Assembly and general integration takes place in the same hall as the Ariane 4 fairings.
5, 4, 3, 2, 1, start.
Separation tests on the complete fairing were carried out in a vacuum environment. The qualification process was completed by acoustic and static testing. The various elements of the upper composite were assembled for electromagnetic compatibility, acoustic and separation tests. Built to handle 10 launches a year, the Ariane 5 launch site, ELA-3 in Kourou, is close to the launch facilities for Ariane 4. It was specially designed for the new launcher and covers an area of over 300 hectares. The site has two main zones. The launcher preparation zone, which contains the launcher integration building, where the cryogenic main stage, vehicle equipment bay, storable propellant stage, and two solid propellant boosters are mated. The final assembly building, where the payloads are installed. Inside the Speltra structure and fairing. The preparation and launch control center. And production plants for liquid hydrogen, liquid oxygen, and liquid nitrogen. The other zone is the Ariane 5 forward launch zone, connected to the preparation zone by a twin railway track, which is used to move the assembled launcher into lift-off position on a mobile launch table incorporating the umbilical mast. The ELA-3 site is designed for maximum simplicity and minimum vulnerability of the forward launch zone. Development and qualification tests on the Vulcain engine, initially with battleship version tanks, were carried out in the launch zone in 1994. The cryogenic stage underwent a very comprehensive program of tests. 5 development tests on flight structures were carried out in 1995, followed by 2 qualification tests in flight configuration. Total burn time for the stage-level tests was almost 5,000 seconds. Use of the launch zone for development tests reduced the requirement for major dedicated test facilities in Europe and contributed to qualification of the ELA-3 site. In 1996, Ariane 5's maiden flight with an unmanned version of the launcher placing 4 ESA scientific satellites in orbit. After the 2 Ariane 5 qualification flights, ESA will entrust the Ariane Space Company with operational exploitation of the new launcher, which is designed to provide Europe with continuing access to space for its own needs and those of all its customers throughout the world.